Welcome you all for the structural analysis lecture series. So in this session, we'll try to discuss about this CDT2, that is different methods of analysis, structural analysis, that is displacement methods of structural analysis and application of slope deflection method. So different displacement methods and application of slope deflection method. Myself, Mr. Ashikar, Assistant Professor, Department of Civil Engineering, Kitswara. Right. So these are the two lecture outcomes. So after completion of this lecture, student will be able to identify the displacements methods, identify the different displacement methods, and the student will be able to understand the applications of this slope deflection method. Understand the application of slope deflection method for various different structures. Yeah, right. So any structure, it can be analyzed by using two different methods. Any structure or structural member can be analyzed by using any for the analysis of any structural member. We have two different approaches. First one is force method of approach and the displacement method of approach. So two ways we can able to analyze. First one is force method of approach and the second one is displacement method of approach. Okay. So in the force method of approach, here the basic unknowns are the forces. Forces are the basic unknowns. So the force method of approach can be used, can be adapted or used for structural member when its degree of static indeterminacy is less as compared to degree of kinematic indeterminacy. In that particular situations, the degree of static indeterminacy of the structure is less than that of degree of kinematic indeterminacy. That means kinematic indeterminacy is more as compared to degree of static indeterminacy. In that particular situations, you can use this force methods of approach. This force methods, first method is method of consistent deformation, theorem of least virtual work, and column analogy method, and flexibility matrix method. So these are the four force methods. Here in these force methods, the basic unknowns are the redundant forces. Basic unknowns are the redundant forces. So coming to displacement methods, in the displacement method, the basic unknowns in the displacement methods are the displacements, that is slopes and deflections. Slopes and deflection. Theta and delta are the basic unknowns. Basic unknowns in the displacement methods are displacement, that is theta and delta are the basic unknowns. First, we will identify the basic unknowns theta and delta from this theta and delta, that is the slope and deflection. From the slope and deflection, I'm going to calculate the moments, final moments. Okay, so moments we're going to calculate. So analysis is nothing but finding unknown moments, and forces, unknown forces is nothing but analysis. So different methods we have in the displacement methods. They are, first one is slope deflection method. Second one is moment distribution method. Third one is Carney's method. First one is a slope deflection method, it's unit 1, and the moment distribution method, unit 2, Carney's method, unit 3, and this is stiffness matrix methods you can going to learn in advanced analysis of structures. Advanced analysis of structures you're going to learn the stiffness matrix. Okay, so we have 4 displacement methods and 4 force methods. So we can use any of the method for analyzing the structure. You can use any of these methods, but if the static indeterminacy is less as compared to the kinematic indeterminacy or degree of freedom, then by using force method of approach it is easier as compared to displacement methods. So the static indeterminacy is less, as compared to kinematic indeterminacy, then we can use force methods of approach. That means we can easily solve by using this force method of approach. The static indeterminacy is less than that of kinematic. So in other words, if the kinematic indeterminacy is less than the static indeterminacy. Kinematic indeterminacy is less as compared to static indeterminacy. In the situations, we can able to use. So it is structure can be able to easily analyze by using displacement methods of approach. Okay. So these are the different methods. So now we'll discuss about the slope deflection method. Slope deflection. Okay. In this slope deflection method, in this method, the basic assumption is that the deformations are only due to bending deformations. Deformation is nothing but in the slope deflection method, basic unknowns are, as I told you in the previous slide. In the slope deflection method is a displacement method. In this displacement method, the basic unknowns are theta and delta. Displacements are the basic unknowns. Okay. Similarly, in the slope deflection method also, the basic unknowns are displacement, that is theta and delta. Yes. So for the solving the problem by analyzing the structure by using slope deflection method of design, the basic assumption we need to remember that in this the deformations are only due to bending. The deformations are due to bending only. Structural deformations is due to only bending. That means axial deformations are neglected. That means axial deformations of the members are neglected. That means axial deformations. So let us suppose it's just member is subjected to axial force. The axial deformation can be calculated. Delta L can be calculated by PL by A. This axial deformation is neglected. Only the deformation due to bending are considered for the analysis of these structures. So let us suppose if you take a beam, it is subjected to uniform distributed load throughout its length. Is acting vertically downward direction. The load is acting perpendicular to the axis of the member. In that situation only. So here we will going to develop a rotation and a displacement. So delta will be there, theta will be there. If it is simply solved beam, theta will be there. Theta and delta will be there. Okay. Only these deformations are considered in slope deflection method of design. So this displacement, axial deformations is neglected. So this is an axial deformation. This is flexural deformation, bending. Deformation due to bending. This is axial deformation. So these axial deformation effects will be neglected in this analysis, slope deflection method of analysis. So now we'll see the equation slope deflection method equations to solve the find out the final end moment. So in slope deflection method, final end moments can be calculated as final end moments. So end moments. So let us suppose we consider a beam, continuous beam A and the B. This is a continuous beam AB. It is continuous toward this side as well as this side. It is subjected to a load here. A beam is subjected to some pattern of load. So then there will be some moments will going to develop at A as well as B. So these are called end moments. Moment at A and moment at B, those are called end moments. These are hogging moments. So due to loading, the moment is sagging. Due to reaction, that is moment reaction, the moment is hogging moment. So this is hogging moment and this is hogging. Okay. Now, so we will discuss. Generally, in general, end moment developed three ways. First one, due to loading. If you apply load on a beam, end moment will going to develop. And the second situation where the end moment will going to develop is when the settlement, in the case of settlement of support, with respect to one support, if another support settled by delta, then there will be chance of movement. So this situation we are represented here. This is the situation. With respect to one support, if another support settled by delta, then also end movement will going to develop. That developed end movement MAB will be equal to 6 EI delta by form of calculation of end movement. MAB will be equal to 6 EI delta by 6 EI delta by L square. MBA will be equal to 6 EI delta by L square. So both are clockwise. Both are anti-clockwise. Sorry, both are anti-clockwise. The second situation, first situation is due to loading. Due to loading, the moment developed will be considered that is considered as fixed end moment. So due to loading, whatever the moment developed at end, that is called fixed end moment. Fixed end moment is depends upon applied load, whether it is a load is acting point load, unit point load, or it's 2-point loads, a uniform distributed load, or uniformly varying load. So depending upon type of load, the fixed end moment will going to differ. Fixed end moment will going to change. Okay, if it is, so first situation is fixed end moment. So this is the total final end moment can be equal to moment due to loading plus moment due to settlement of support plus moment due to a rotation of support. If the support will rotate by theta, then also fixed end moment will going to end moment will going to develop. End moment will going to develop in the field. Now the final end moment can be calculated as, so final end moment will be equal to moment due to loading. Here we are calling this as fixed end moment. Fixed end moment plus final end moment will be equal to moment due to loading plus moment due to rotation theta A and theta B. Moment due to theta A and rotation of support A or support B. Moment due to support A or support B plus moment due to displacement of support. That means settlement of support. Moment due to delta. Moment due to theta as well as moment due to delta. Settlement of support. So these three ways moment will go, end moment will go into develop. So now the final end moment MAB can be written as, so due to rotation of support, the end moment will be 4EI by L, 4EI theta A by L at support A, at B 2EI theta A by L. So here support A is rotating. Support A is rotating by theta A. So ఇక్కడ support A దగ్గర rotation ఎంత ఉంది theta A ఉందనుకుంటే, then the moment at A will be 4EI theta A by L, moment at B equal to 2EI theta A by L. You remember this. Support rotate by theta, support rotation at support A is theta A, then the moment developed at A will be equal to moment developed due to rotation of support will be equal to 4EI theta A by L. At B, only support A is rotating, but there is a moment is also going to develop at B also. That is 2EI theta A by L. This is from carryover theorem. The carryover theorem you will study in the next unit. Okay, that is 2EI theta A by L. Just remember this moment. End moment due to rotation of support at B will be equal to 2EI theta by L. Similarly, if support B rotate by theta B, support B rotate by theta B, then in the clockwise direction. This is also in the clockwise direction. This is also in the clockwise direction. Then the moment developed at B will be equal to 4EI theta B by L. Moment developed at A will be equal to 2EI theta A by theta B by L. Theta B by L. Now if support B settled by delta, then MAB equal to 6EI delta by L square, MBA will be equal to 6EI by delta L square. If you add all this, you are going to get MBA. If you add all these, you are going to get MAB. If you add all these, you are going to get MAB. So now, if you simplify this, you can get MAB will be equal to, so this is called slope deflection equation. MAB equal to 2EI by L into 2 theta A plus theta B minus 3 delta by L plus fixed rate moment due to applied loading. So this is the equation, slope diffraction equation. And similarly, MBA, so moment at A can final end moment at A can be calculated as 2EI by L into 2 theta A plus theta B minus 3 delta by L plus fixed end moment at AB. So MBA can be written as MBA will be equal to 2EI by L into 2 theta B plus theta A minus 3 delta by L plus fixed end moment BA. So this is the two slope deflection equations. Okay, by using this slope deflection equation, we can able to write this slope deflection equation for particular beams. Okay, so now as we discussed the fixed end moments, so fixed end moments are developed due to applied load. So different conditions are there for the calculation of fixed end moments. So if a beam is subjected to fixed beam is subjected to point load at center, fixed beam subjected to a point load at center, then the deformed shape something like this. So beam will deform like this. That means this deformation is arrested here. This fixed end moment is arrested. The moment at this fixed support is arrested the deformation. That means it is try to moving the beam in the upward direction, but applied load is moving in the downward direction. That's why it is creating sagging moment. It is creating sagging moment at the support. Okay, so because of this, MAB moment at MAB is acting anti-clockwise direction. MBA is acting in the clockwise direction. You can see this is clockwise direction. MAB is anti-clockwise direction. MBA in the clockwise direction. Now see, if a fixed beam subjected to a point load at the center, then fixed moment will be equal to PL by 8. This is negative PL by 8. This is positive PL by 8. Negative PL by 8 and that is positive PL by 8. So this is fixed beam subjected to point load at the center. Then the bending moment at MAB will be equal to minus this P, then PL by 10. PL by 10. Then MB, let us suppose this is A and this is B. MAB will be equal to minus PL by 8. MBA will be equal to plus PL by X. This is because here we are getting clockwise, this is anti-clockwise and this is clockwise. Okay, so this is PL by 8 anti-clockwise, PL by 8 clockwise. So if it is subjected to a same fixed view subjected to eccentric point load, MAB is equal to minus PAB square by L square. MBA will be equal to PBA square by L square. Okay, if it is subjected to 2 point loads, MAB will be equal to minus 2 by 9 into PL. MAB, that is MBA will be equal to 2 by 2 PL by 2 by 9 into PL. 2 by 9 into PL. Next, if it is subjected to uniform distributor load, fixed view subjected to uniform distributor load, then the fixed moments at A, MAB will be equal to MFAB will be equal to MFAB, generally called MFAB, fixed moment at AB, MFAB will be equal to minus WL square by 12, MFBA will be equal to plus WL square by 12. This is very, very important, plus WL square by 12. You need to remember these three formulas. First one, and this is second one, PL by 8, PL by 8, and this is one, third one, eccentric point one. PAB square by L square, P A square B by L square. So these are three formulas you need to remember. So just focus on these three formulas and just look at the other formulas also. Yes, try to remember. At least you remember these three formulas so that you can solve easily. So these formulas not only in this chapter but also the second and third chapters, these formulas are useful. So try to remember these three basic formulas. So fixed moment due to loading. These are fixed moment due to loading. So this is the one reflection spot. The slope deflection method can be used to analyze dash and dash type of beams and frames. So it is slope deflection method is used to determinate as well as indeterminate beams and frames. Slope deflection method, the relation established between moments at the ends of the member corresponding to its slopes and deflections. Slopes and deflections. The slope deflection method is assumed that all the deformations are due to you just tell me deformation is due to bending only. That means axial deformations are negative. Okay. Axial deformations are negative. Axial deformations are negative. Yeah, this is one reflection spot. Now we'll see the applications of slope deflection method. The slope deflection method can be used for determinate beams, determinate structures, so determinate structures, and it is also used for indeterminate structures. That is continuous beams, and frames, continuous beams and frames with sway and without sway, continuous beams with sinking of support, without sinking of support, and the frames with sway and without sway. So these are this type of problems can be analyzed easily by using slope deflection method. First one is, but it can be used for determinate structures. It can also be used for indeterminate structure, and it is used for frames also. It can be used for frames, sway and non-sway frames also. Okay, for analyzing the sway frames and non-sway frames, we can use the slope deflection method. So here we have one lecture level practice problem. Here asking to calculate fixed end moments to determine the fixed end moments for the beam as shown in figure. So this is uniform distributor load is there. So you need to calculate fixed end moment due to loading as well as uniform distributor load and eccentric load. So as I told you, due to uniform distributor load, MAB will be equal to MFAB will be equal to minus WL square by 12. MF